introduce you Jacqueline Bloch from the Center for Nanoscience and Nanotechnology of Palaiseau, C2N. Jacqueline is an expert in nanoscience. Namely, she studies the interaction of photons with matter, typically semiconductors. And here the key word is polariton, and which is a kind of excitation of the photons. She will explain. Sorry. Quasi-particle. Okay. And Jacqueline is a member of the French Academy of Science since 2019, and her work has been awarded by many distinctions. I cite the CNRS Silver Medal. And last but not least, the fact that we are in a Claude Bloch amphitheater and that we have Jacqueline Bloch is not a kind of coincidence. She's the daughter of the first head of IPhT, well, it was called the Service de Physique Théorique at that time. And so we are doubly happy about this seminar. The title of the seminar today is quite intriguing. Is Quantum Fluids or Light in Semiconductor Lattices. So enjoy.
Thank you very much for the introduction. So for me, it's also a great pleasure to be here. It's my second time I speak in this amphitheater. But it's true that I am the daughter of Claude Bloch, and actually there is my picture in the corridor. I changed a bit since that time, so people are not sure that it's me, but yes, it is. So it was, I'm in the back of my father, and we were in Les Ouches. So I attended Les Ouches school, summer school, when I was not even able to walk, actually. So thank you very much for this invitation. So when I started to think about what I was going to tell you, I was a bit frightened because I know that you work in super high dimension, like 11 dimension, that you work on very complex physical phenomena where sometimes there is no experiment to do, to test, and there will never be, or I don't know. And I am only 2D, sometimes 1D, even 0D. And it's much more easy, I think, to understand. But on the other hand, it's a completely different topic. And so at the end, so I thought a lot, and I was a bit blocked. Actually, that's why I did not send you my abstract, because I did not know what to tell you. And finally, I say, okay, let's do a seminar as usual and try to make you understand what I'm doing. This is going to be also very exotic for you. So let's see if I manage to give you a flavor of what we are doing. So I come from a lab which has been got installed on the Paris-Saclay plateau a few years ago. So it's called Center for Nanoscience and Nanotechnology. You are most welcome to visit us if you are interested. And so you can see here the logo of this of the lab, and it's actually a schematic top view of the building. And the green square that you see is the clean room of the lab. So it's a place which is extremely clean and where we can fabricate, grow crystals, atomic layers by atomic layer, and then etch these structures at the nanometer scale. And then in the rest of the lab, there are people doing experiments, essentially transport experiments, so making current flow through these structures and trying to measure interesting properties, or people doing optics, so sending light on this material and try to see, to study light-matter interaction. And then there are people doing very fundamental physics, trying to see new phenomena, and other people working more on device-oriented application. And so my group, and you can see the people here, so there are people producing the sample, so they are not really my group, but they are very close collaborators, and then people doing. So what we do is optics. So we do experiments with light, and we do fundamental research. That's what we are interested in. So our source of inspiration is, it works, really macroscopic phenomena that occur in condensed matter physics that you may probably be familiar with. So for instance, superfluidity, the fact that if you have some liquid, some particular liquid, and you cool them down to very low temperature, they start to become, to flow without any friction. So this is superfluidity that you can see, for instance, in helium-4. You can also, for example, with cold atoms, cool them down to super low temperature, and you can observe Bose-Einstein condensation, which is phase transition. And below this temperature, the whole cloud of atoms behave really like a macroscopic wave, a matter wave that you can make interfere, that can also become superfluid, and with which there is really very interesting physics going on. Then you can we also consider really solid-state systems, like, for example, graphene, which was discovered not so long ago, which is really an atomic layer of carbon atoms organized in such a honeycomb lattice. And the band structure of the levels of electrons in these materials are very exotic and provide the material super interesting properties. And these properties somehow are related to topology. So there is a way to really understand and explore this material using topological argument. And there is another phenomena which is really the emblematic example where topology plays a role, which is the quantum Hall effect that you can observe when you place a 2D system of electrons in a magnetic field. And you measure the whole resistance, so the transfer, you try to have currents flow through the structure, and you measure the voltage that can occur at and the resistance, the transverse resistance. And if you go to very low temperature, what you observe is that the classical linear slope, the variation of the resistance with the magnetic field, starts to develop some stairs, some plateaus. And when you look at the resistance on this plateau, it is only related to E and to H bar, and with some fractions, so to some integer. So it is actually fascinating, and what you can show is that this integer is really a topological invariant, and the fact that there is such a quantification is related to topology. And after that, some materials were discovered which are called topological insulator, which are materials which are insulating in the bulk but can transport currents through the edge. And actually, you can show that in the quantum Hall effect, the current flows through quantized channels on the edge of the structure. So some field has developed in the recent years, which is based on these fundamental questions. Can we emulate this physics with light? Can we fabricate some lattices? Can we conceive some samples where light could show some of these properties? So, for example, here you have this experiment which is really beautiful, which is based only on silicon ring resonators. I'm very bad with this pointer. I'm going to use this one. So light goes into these resonators and can couple, go from one resonator to the next. And actually, it was possible to reproduce, to emulate the physics of the integer quantum Hall effect. So light actually goes through the edge of the structure, and actually because this edge state is governed by topology, it's very robust. And you can make any kink in the interface, the edge state will remain there, and light will propagate without any backscattering. Another example is Bose-Einstein condensation of light in a semiconductor. So we call this kind of nonlinear light cavity polariton. I'm going to go back to that. And so it was possible actually to show that above a certain excitation power, suddenly you form a macroscopic state in the lowest energy state, and this behaves as a nonlinear macroscopic wave with which you can play. So then it's nice to be able to reproduce condensed matter physics, but what is nice also is that there are new ingredients in photonic systems that you can play with and that allows to go beyond what you can find in solid-state system. So for example, in this example, there is a gain and loss. So you can play with what is called PT symmetry and actually see the emergence of topological states just by the modulating in real space gain and loss. Another mechanism that you can find in photonic systems is lasing. And so you can here engineer a topological edge state and trigger a laser into this lasing mode, into this edge state. And so light in this coherent lasing mode will rotate along this edge state. And here there is a waveguide, and so light will come out only in one direction, in this direction. Actually, in this system, you need to break time reversal symmetry, so you apply a magnetic field. So that imposes the rotation clockwise or anti-clockwise. And if you reverse the magnetic field, you get the other direction, and light will go to the others. Okay? So it's just to show you that we are interested in this physics coming from solid-state systems, but we want also condensed matter, but we want also to go beyond using the different ingredients that can be offered by a photonic system. And so the family of systems I will be interested in are called driven dissipative nonlinear photonic system. So typically you can imagine that we have an array of sites which are formed by small cavity where photons can be trapped. And so you have a photon can hop, so there is a coupling constant between different sites. There is some interaction, so we will see where this comes from, but if you put two photons in the same site, there is some interaction energy. And then there is loss from each site, so we call the loss rate gamma. So this means that if you want to introduce to reach a steady state, since photons always escape from the cavity, you need to pump it continuously to refill the system with particles. And so we will see that there are two ways of pumping the system. One which we call incoherent drive, which means that we don't impose any phase, any coherence in the system, we just inject particles into the different sites. And there is another way which we call coherent drive, which means that we can actually send a laser light, a coherent laser light with amplitude f, frequency omega p, and even phase phi, and we can inject photons independently in different sites and control the density, the energy, and the phase of photons that we inject in the system. And then we want to look at possible nonlinear steady state. So the system can be driven in the linear regime. So in the linear regime, you neglect completely interaction energy. Then you can go into nonlinear regimes, but treat the system in a mean field approximation. So you neglect correlations between the field in the different sites. Then you can start to go beyond mean field by considering noise, fluctuations in the pump. And then you can go into quantum regimes where you really expect to see quantum correlations between the different sites. Okay? So there is an increasing difficulty in describing theoretically the system and also in performing experimentally the experiments. Okay? So the outline of my talk will be the following. So first I would like to really describe, introduce a lot the system so that you can follow a bit what I'm doing. The beauty of the system is really that we can collect photons and image the physics directly. So most of the picture I will show you are raw data. This is typically raw data. This is raw data. So we will, in the second part, so what I want to describe is really to focus on two recent results that we got. One which is related to Bose-Einstein condensation. And so here this is a 1D condensate where we could show that these condensates, which are out of equilibrium and they are open systems, belong to a different universality class than their equilibrium counterpart, which are cold atom, for example, condensate. So this is what I want to describe in detail. And if we have time, I will show you quickly a recent experiment which is related to topology. And so I will show you that thanks to the way we measure the system, we can actually measure experimentally topological invariant, like Berry curvature or Chern numbers. So that's what maybe I will have time to describe. And so if you want during the talk to ask questions, please don't hesitate to interrupt me. It's better if we can discuss together even during the talk. Okay, so what we want to do is work with cavities. We want the cavities to be the most controlled as possible. And so to do that, we use a system which has been extremely well developed for optoelectronic devices. So actually, in any mobile phone or the red LED that we use or the red lasers, they are based on gallium arsenide, aluminium gallium arsenide. And so the technology to fabricate this sample is super nicely developed. So we can actually grow layers by layer, atomic layer by atomic layer, gallium arsenide layers, aluminium gallium arsenide layer, and we can really do a sandwich of any layers we want. And so we use that technology to grow super high reflectivity mirrors. And so typically the structures that we use is made of two high reflectivity mirrors, which are here, which are very thick actually. And then in the middle, there is a layer which is a bit thicker, which defines the cavity. And so photons can oscillate, so can be confined between the two mirrors and form a standing wave. And this is a resonant mode. And so there are several modes depending on the wavelengths. So if we consider, for example, one mode, here it's depicted here, you know from very basic courses that if you send the light vertically, there will be some resonances. And then you can change the angle of incidence. So light will oscillate but with a small angle, and the resonance will be at a slightly different energy. So if you look in detail, so angle is equivalent to k vector for light. Okay, k equals 0 is like this, and then there is a larger k. And so you can plot the energy of the resonance as a function of the angle or as a function of the in-plane wave vector. And if you look close to normal incidence, what you find is that you get a parabolic dispersion. And a parabolic dispersion looks exactly like the energy of a free particle, h bar squared k squared divided by 2m. And so we define a mass for our photons. It means that the motion of photons in the plane, so instead they don't go straight, they do this kind of round trip, it is really equivalent to the motion in 2D of a massive particle. So for us, photons have a mass. You get used to it. Of course, this is only for small values of k. If you go to very large values of k, you recover a linear dispersion for photons, okay? So then what we do is we insert inside the cavity another material which will form a quantum well for electrons which are traveling around in the semiconductor. So it means that here this is a trap, a 2D trap for electrons. And so these electrons, do I have the, no, yes. Here, so this quantum well form a trap for electrons, and so also so this is in the conduction band of the material, but also a trap for holes, which can be generated if you send a laser. You can have an electron going from the valence band to the conduction band, and then you end up with an electron-hole pair. So these electron-hole pair, you can excite them. This is an excitation of the material. They live for a certain time. They are called excitons, these electron-hole pair, and they can move in the plane of the quantum well, and they are also described by h bar squared k squared divided by 2m, but here the m is the mass of the electron plus the mass of the hole, which is super heavy, 5 orders of magnitude heavier than the photon. So if you plot the energy of the exciton, it looks completely flat because of this large effective mass. These excitons, they live for a certain time, and then they recombine. And so what we do is we design the structure so that the emission of the quantum well is quasi-resonant with the photon mode. So that the exciton will take its time, certain time, not long, it's in the picosecond time range, and then emit a photon which will oscillate within the cavity long enough to be reabsorbed and then re-emitted, and so on. So at the end of the day, we have really two harmonic oscillators which are coupled with some frequency which we call the Rabi frequency. And if we compute the eigenstate of the system, they are really mixed exciton-photon states which we call polariton. And these are the bands that you get from this strong coupling. Okay? So, why are we interested in this cavity polariton? Why are they really interesting? It's really because they are a linear combination between the exciton and the photon, and they have properties coming from both sides. From the photonic component, you get dissipation, because it's the photon that will escape. Also, polaritons, so photons, confined in a high Q cavity, they are big objects. You can understand that very easily. You know that there will be a narrow resonance in K space. And so if you are very narrow in K, it means that you are broad in real space because Mr. Fourier is watching us all the time. So this means that if I want to confine laterally and to engineer potential, a lattice, and so on for polaritons, I don't need to go to the nanoscale. Micron scale is enough. You can see it here. If I make a finite system, I'm going to quantize K according to the inverse of the dimension of the structure I use. So if it's 1 micron, you see I will quantize K, and you see that the first level will be already at a significant confinement energy. So this is very convenient from the technological point of view, because I'm going to play with micron-sized structures, which is much easier to realize. So this is why I say that it's the photonic component that we will confine in microstructure. Then we will measure the photonic part coming out from the structure, and you will see that this enables to image the polariton states in real space, in K space, and to do all kinds of experiments. So these are massive photons confined in a cavity, but with some matter part, the exciton. Excitons are an electron and a hole pair bound by Coulombic interaction. They are fermions, and they interact with each other. When you take two excitons, there is some Coulombic interaction dominated by exchange energy. So there is interaction, this U that I introduced in the first slide. And because of that, we have a huge nonlinearity. So you have not only these two harmonic oscillators, but then you will add some interaction with ADAG, AA, of different particles, different states. So this provides in the mean field a Kerr nonlinearity, which is super large, like several orders of magnitude larger than in regular nonlinear crystal. And that's why we can go into highly nonlinear regime and, for instance, observe superfluidity. The exciton can also provide gain, so we can laze in some mode. And then what is super important for topology, for example, is that exciton, when you apply a magnetic field, they acquire a Zeeman splitting. One state emitting sigma plus and the other sigma minus. So that our polaritons, these photons, confined inside the cavity, they also acquire a very large Zeeman splitting under a magnetic field. So this allows to break time reversal symmetry. Okay, so how do we measure them? As we said, we measure photons coming out, and we can look at photons coming out as a function of energy and angle. This is very easy experimentally. And then you directly see on the screen of a CCD the two branches. This is raw data. You can look in real space. So this is a honeycomb lattice emulating the physics of graphene. And we see the lasing mode, which comes from each individual pillar. This is actually a condensate of light in a honeycomb lattice. We can do interferometry. So interfere the emission either with a reference laser or with itself, selecting different configuration. This allows to image vortices and solitons. Once you have a superfluid, you may be interested in turbulence and seeing topological defects. So we can measure the first order coherence or the emission statistics. So we have really access to everything that is going on in the system, just monitoring photon escaping from the structure. Are you still there? Yes, cool.
Can you say a few words about how in the honeycomb picture, how they are coupled?
I'm going to go to that very quickly. I think I will stay because just talk about the introduction. In a few slides, and then if you have questions, you can come back. Okay, so as I said, these polaritons became famous. First, very famous in the mid-2000 with the demonstration of Bose-Einstein condensation. I'm going to go back to this experiment. And then there was the demonstration of superfluidity, which really showed that something is going on. So the way the system is, so here it's a planar cavity. Yes?
I thought I heard you mention that the polariton is a fermion.
No, it's a boson. Did I say something like that? No. It's made of, the exciton is a composite boson. It's an electron and a hole, so it's a, and then it's coupled to light, which is a boson, so these are bosons. So you have to imagine that we are looking at a planar cavity, just two mirrors. We are looking from the top. This is X and Y. And we are sending a plane wave inside the structure. So we are, imagine that all the stage is a cavity. I send a plane wave and light will propagate. And I look from the top. If it's a plane wave, it's constant in intensity. So if I look from the top, I just see a constant illumination, something which is white, but which is just no structure. But then Cristiano Ciuti and Jacopo Carusotto imagine an experiment where there would be a defect in the flow. In the middle, there is a defect. So the plane wave is here. There is loss in the system. And then we describe the amplitude of the field by a Gross-Pitaevsky equation. So there is kinetic energy. This is the mass of the photon. There is potentially some potential, which is, for example, the defect in the middle of the way. Interaction in this equation, and that's it. So if you are in the low density regime and you can neglect interaction, then you see just interferences because there is some scattering between the incoming beam and light which is scattered by the defect. Okay, this is a large audience, but it's very clear then. And then the idea is that if you increase the amplitude of your plane wave, you start to have the role of this guy, which is going to be important. You actually renormalize the dispersion because of interaction. I'm not going to go into the detail. And at the end of the day, you reach a regime where there is no states anymore at the energy of your pump to be scattered to. And so there is no scattering anymore, and light will just go straight without being altered by the defect. And this is the superfluid regime. And then in this regime, there is a speed of sound. So it's a sound made of oscillation within your fluid. You can go into supersonic regime and see the Cherenkov cone, and then you can start to look at the nucleation of vortices and solitons in the wake of the defect, and there is a lot of physics which has been explored after this seminar paper. Okay, so if you want to see the experiment, this is in this paper from Alberto Amo, and since then, this system, instead of talking about cavity polariton, we talk about quantum fluids of light because it looks like a fluid. Okay? So the specialty of our work is to build lattices. So we use the clean room to actually design some masks. So we imagine that this is a planar cavity at the beginning. We deposit on top of the cavity some small mask, and then we send the plasma and destroy everything that is not protected by the mask. And so at the end of the day, for example, you get an array of this kind of micropillars. And they are not coupled to each other. In each of these pillars, you have light which is confined laterally by the index of refraction and oscillating vertically between the two mirrors. So if you probe one of these micropillar, you send a laser beam, for example, and you look in transmission at the different resonance that you can see. You see some discrete modes because light is completely confined inside these structures. And so this is real space and energy. And you see that the lowest energy mode has a maximum at the center along this direction. And then there is another mode which has two lobes, and they are actually out of phase. This is the second mode, and so on. And since we are going to build lattices exactly the same way using a time bending approach, so exactly the same way you construct the band structure in a crystal. You take an atom with its elementary orbitals, and then you take another one and you couple the orbitals to form a molecule, and then you take more and you form bands. We are going to do the same, and so in analogy with the orbitals, we call this mode S mode, and this one P. This is Px, and there is another one in the orthogonal direction, which is Py. So then, if we take two of these pillars, so you see the coupling is really not an evanescent coupling, it's really a structure which looks like an 8, and you see that the distance between the center is smaller than the diameter. So it's really just the shape of the resonator. You can describe it actually as two s orbitals coupled to each other. And you see that the S mode becomes a bonding and anti-bonding mode of the S mode of each pillar. And then the P mode, they also become a bonding and anti-bonding between the PX modes and so on. Okay? And so then if you make a 1D structure, a full array of micropillar, I'm going to try to use this one, you see that the modes, the light is completely delocalized over the entire structure. And if you look in K-space, you form a band which is completely governed by the distance between the sites that you have chosen. If you make the coupling big, you will have a wider band and so on. And this is a band for the S mode and a band for the P modes. And then, if you want, you can play with the laser beam, excite each site with a given phase and a given amplitude, and play with this discretized Gross-Pitayevsky equation. Okay? This is a scalar model. I'm not going to go too much into the detail, but you can also emulate the physics of the spin, taking into account the polarization of light. Okay, so there is sigma plus or sigma minus, or horizontal, vertical, and this, except that we plot the spin on a Poincaré sphere, it looks like a Bloch sphere, and you can use that to emulate the physics really of electrons in a crystal. So this is the playground. Are there questions? Oops, I'm not finished. I wanted to show some example. Like, for example, this is a 1D lattice where there is a phase frustration. You have 3 atoms per unit cell, 3 sites per unit cell. So you have 3 bands. The lowest band, all the sites are in phase. The upper band, all the sites are out of phase with their neighbor. And then the middle band, each site is supposed to be out of phase with the second neighbor, so that this guy doesn't know who to follow. And actually, it doesn't follow anybody. There is a 0 of the eigenmode on this site, so that you form a flat band. And so you can see directly, looking at the emission of such a pillar, and you see that there is a beautiful flat band. And then if you select this energy and you look at where the light comes from, this is what you see. You see that these are S modes with the center in the maximum in the center, and you see that the B sites are dark. Okay. And then we have done a lot of work on honeycomb lattices. So this is a honeycomb lattice of coupled pillar. It's quite difficult to fabricate because we need to dig holes, very vertical and very deep holes to fabricate the structure. So here the technology starts to be quite complex. And then we can look at the band structure. So this is the band structure of graphene. Actually, you have 2 atoms per unit cell. So you have 2 bands. And the specificity of this material is that the 2 bands, they touch each other at the edge of the Brillouin zone, and they form these Dirac cones, Dirac physics, because there is a linear dispersion. So here is a band structure that we can measure. So here there is this is a 2D lattice, so there is Kx and Ky. So we can plot the dispersion in 3D, but here I show you just a cut for a given Kx, which has been chosen so that we intersect these 2 Dirac cones. So I don't know if you see them well, but they are here. So you see the bands coming from hybridization of the S modes. And so we see these Dirac cones. And then for free, we have also all the bands coming from the P bands, the P mode. And here you have 4 bands because we have 2 atoms per unit cell and 2 orbitals per site. So this is 4 bands. The lowest band is quite flat. Then you have new Dirac cones, and the upper band is a bit more complicated. So then you can do a lot of things with that. You can distort the lattice, you can look at many different things. So this has triggered a lot of theory proposal, the fact that we can fabricate artificial lattices. And so we have been working a lot on that. And if I have time, I'm not sure I will go back to that. So let's go to KPZ. So KPZ concerns this experiment that I showed you, where we pump the system non-resonantly. So you don't want to know the details, but essentially we pump the system with a laser, which is highly detuned with respect to all these resonances. So you excite a semiconductor, you create plenty of electron hole pairs. They lose energy emitting phonons, vibration of the crystal. You don't care. It's like a rain of excitation that will populate your bands. And you lose completely the memory of the polarization, the energy, the phase, whatever of the pump. It's an incoherent pumping. And then you have, if you populate your polariton bands, and if you manage to get an occupancy larger than 1 in one of these states, you will trigger stimulated scattering into this polariton state, and you will see an exponential growth of the population and form a condensate. That's what these people did. This was a group of Grenoble together with a group at EPFL. And you reach a steady state when the pump overcomes, balance the decay, and you get a condensate when the gain overcomes the loss. And this is some words that look really like a laser, actually. And this is actually a polariton laser. So the question was, does your system look really like a BEC, or the fact that it's an out of equilibrium system, that it's driven dissipative, does it make a difference? So to understand a bit what is going on, so the system, as I told you, is very complicated. And so what people did at the beginning is just to simplify the problem. And just consider that you have a big box, which is called a reservoir, which is pumped by your laser or your current or what you want. This reservoir can emit into leaky modes. It's also open. And it can populate by stimulated scattering a given state, which is your condensate, which has some decay. So for the condensate, you write this Gross-Pitayevsky equation, and it is coupled to a reservoir, which is pumped and which has some decay or population of the condensate. Okay, you have these two coupled equations. And what is important is that there is noise also in the system because of the pump and of the dissipation. So, using these two equations, in the mid-20s, 2000, people worked very nicely and could describe everything about the experiments that were proposed. It was sometimes very qualitative because, of course, we don't take into account all the details of the physics, but the macroscopic picture was there. And then what is very interesting is that it took 10 years before some theoretician, some Ehud Altman, you may know, coming from cold atom physics, and Sebastian Diel, or other Michiel Wouters, coming really from polaritons from the beginning, got the idea to play a bit with this equation. So they did a transformation separating density and phase of the condensate. They made some assumption about the time scale for density and phase fluctuation, and then they could show that actually the phase, theta of x and t in 1D, theta of x, y, and t in 2D, obeys to this equation. And this equation is actually very celebrated. It is the Kardar-Parisi-Zhang equation. So this was a surprise that Kardar-Parisi-Zhang universality was hidden in our polariton condensate. So how can we, what is this equation? So this equation was written in 1986, and it was written to describe the growth of out of nonlinear systems which are out of equilibrium. So typically the frost on a window, or liquid crystal interfaces. So systems where you feed it and you look at the growth of the interface. And in this equation, there is a diffusion term which tends to make the surface smoothen. And then there is a nonlinear growth term which tends to develop roughness. And there is noise. And usually it's a stochastic, so this stochastic term is taken as a white noise, so a white Gaussian noise. And you look as a function of time at the shape. So h is the height of this interface as a function of x and t, and you look how the height varies as a function of time. That's it. So why is it interesting? It's interesting because what you find is that actually correlation develop a long time. And so this correlation, so it's the correlation between what you measure at time t and position x and what you have measured at 0 time and x equals 0. And this correlation obeys to power law with coefficients which are universal and only depend on the dimensionality. And even more interesting, you can actually show that this correlation, they can be written like this with some rescaled units. And the only thing that is not universal is this coefficient here, this rescale coefficient, and another one which is here. All the rest is universal, and this fkpz is a function which is tabulated, which could be solved analytically in 1D, and it's still an open problem in 2D to solve this model. So here I show you the coefficient, the kpz coefficient in 1D. And then there is another property of this physics is that if you look at the probability to find some height at a given position, so you make a lot of realization and you see what is the probability to find an interface with some given height at a given time and position, you find that even if the noise is Gaussian, the density, the probability distribution is not Gaussian at all, it's skewed. And it's actually related to random matrix theory, which my father worked on actually. And it is described by some Tracy-Widom distribution. So the way to really show that you have this KPZ, I mean, this is one of the signature of this KPZ physics, mathematics more. So what is the link between our condensate and this physics of classical interface? It looks completely weird. Actually, you can understand where the interface is. It is actually the phase front. In our condensate, so if we have a 1D condensate and we make a picture, an instantaneous picture, we have a phase front. And this phase front will have some fluctuation, and this is the interface. And then if you were able to make another picture, 20 picoseconds later, you would see the phase front having some distortion and so on. So the phase front of our system behave as an interface. And because the phase obeys to this equation, we expect to have correlation between the phase we measure, for example, here at this time, and the phase we have measured at t equals 0 and x equals 0. So we expect, if we were able to measure instantaneously the phase, to observe correlation and this critical exponent. The problem is that we are not able to make instantaneous picture at this speed. And so there was a question how to probe KPZ physics if we cannot make this kind of pictures. And so then theoreticians helped us. Actually, what we can measure is the amplitude correlation in the system, so what we call G1. And you can show, so if you want to see the derivation, it's done properly line by line in this paper. You can show that actually, with some assumption that you need to check in the experiment, the G1 is proportional to the mean of exponential E, variance of the phase, and so on. And then if you have small enough fluctuation, you can make a linear expansion and show that the G1 square is proportional to exponential minus the variance of the phase. So what we should look at is minus 2 log of G1. If we measure minus 2 log of G1, we should see KPZ scaling. Okay, so that's what we try to do. So there is another thing that is very important. At least I want to finish KPZ. This is that we are playing with the phase and not with the height. And the phase is a compact variable defined between 0 and 2 pi. So there are some differences. And this is the fact that we may have vortices. So usually in 1D we don't care about vortices because you need 2D to organize a vortex. But here we are actually in an effective 2D system with X being the real space dimension and T the other one. And so it has been shown that actually you can have some defects, some topological defects, which are spatiotemporal vortices. And if these kind of defects are too numerous, they will wash out completely the correlation that we are looking for. So later on, together with our colleagues in Grenoble, we actually calculated and interpreted a whole phase diagram depending on the power, on the interaction with the reservoir, and on the noise. There is a whole phase diagram, and you see that it's only in some certain window that we should see KPZ correlation. Otherwise, we are dominating by other effects. In 2D, it's even worse because we have these space-time vortices plus the spatial, the regular 2D vortices. And so there is actually a debate presently whether it is possible or not to see KPZ. So there are some theoreticians who say, no, it's impossible. And others who make calculation and say, okay, it's impossible, but look, I did simulation and I find it. So I will come back to that later. Okay, so we fabricate, so I'm not going to detail but if we create a condensate here at k equals 0 in the lowest energy state, we have an instability which is going to break the condensate into many different pieces and prevent us to look at large scale correlation. So our condensate is sitting here on top of a negative mass band. So it's really out of equilibrium. We are not at all in the ground state. And it looks like this. This is a real picture of the emission. You see the dimension, more than 100 micron. And this is what the kind of structure we are going to probe. So what we do, what Quentin Fontaine did, is to actually shine an elongated flat top laser beam onto this lattice, create a condensate, send the emission into an interferometer. So one part of the image is going to go like this, and the other one is going to go like this, and then we recombine them. And in this one, there is a retroreflector, which is going to shift the emission, to switch the emission from that direction to the other. So at the exit in this region, we interfere the interferogram with its mirror image. So that, and then we can change the delay between the two images by changing the interferometer, the length of one arm. And so what we find is that if we have equal distance in the two arms, we see fringes here. And so, for example, if I look here, I see interference between this pillar and the one that is located here. Okay, and I probe the spatial coherence over 40 micron. And then if I change the length of the arm, I'm going to see how the coherence between with delta x equal 40 micron is going to decay with time. And then by looking at the fringe contrast, you can actually retrieve the G1. So you do that for many, many different lengths of the arm, and you compute the measurement of G1 as a function of delta x and delta t. So then what are we looking for? We want to look at -2 log of G1 and look if you have the proper scaling. So for example, let's start with delta t equals 0. Delta t equals 0, it's here. And we are going to look at the spatial decay of the coherence. So since it's -2 log of G1, it's an increase, but it's just because of the minus, okay, the coherence decay. And what you are expecting is to see this kind of exponent, and chi is equal to 1/2, so that delta, this is actually an exponential decay. So it's not very specific of KPZ, but if you want to be in the KPZ class, you need an exponential decay in real space. And this is what you get in a small window of delta x. And then we want to look at delta x equals 0. So delta x equals 0 is here, and we are going to look at the coherence along this line. And if we plot -2 log of G1, we should see delta t, a region where we have an exponent 2/3, because beta equals 1/3. This is very characteristic of KPZ, and indeed we have a window here where we have this scaling. So it's not super convincing. I'm just showing that I have, yes, an exponential decay here and a 2/3 decay here. But what about all the other points? So what we did actually is to take all the points that are in this region where we see an exponential decay here and a 2/3 here, and we found that we could actually collapse all the points onto this KPZ universality universal function. So this was quite nice to really show that this out of equilibrium condensate indeed behave as like in the KPZ universality class. So we worked a lot with the theory group of Anna Minguzzi and Leonie Canet, together with Davide Squizzato. And what they did is they actually computed these two coupled equations for different realization of white noise. And since there are so many parameters, we really tried to give them as many parameters as possible from the experiment. And with that, they could indeed reproduce our experiment and indeed explain the different curves. So we got really good understanding of what is going on, and we also got a lot of confidence into the model. And so then I told you that we cannot take instantaneous pictures of the phase, so we cannot probe experimentally, at least for the moment, this probability distribution, but at least we can check if the model who is simulating our experiment does show this kind of skewed distribution. So once we had taken all the parameters of the model, we looked at the trajectory of the phase. So what we do is we take the result of the simulation, we unwrap the phase, so the phase at a given position, and we look how it evolves in time. And so this is what we find. So we have a slope like this, which is just the dynamical phase, exponential minus e omega t. This is going to make a phase, a running phase. And these are examples of trajectories at x equals 0 that the theoretician computed. So you see that there are different families. So the ones that are the most frequent are this one, the small a, and you see that you have just a dynamical phase plus some fluctuations, and the KPZ fluctuations are here. This is the fluctuation. So here, since we plot over a large scale, we don't see them, but this is where we have these fluctuations. And then you see that you have other trajectories which have some abrupt jump. Here you have a few, and in this one you have many. So these ones are very rare. These ones are quite frequent. These ones are the majority one. Okay? So since when you want to compute this probability distribution, you need to renormalize by the mean value. You see that if I have this kind of trajectory, the mean value is going to be very large compared to here, and even larger. And so at the beginning, when people, the theoretician computed the phase, the probability distribution, they found a divergence of the probability distribution, and it was not showing KPZ at all. So we were despaired because we had nice experimental results, and theoretician told us, no, it's not true. It's not KPZ. The variance of the phase does not show G1, yes, but not the variance of the phase. So we were super scared, but that was like that. And then we understood that actually this phase jump, they are phase jump by 2 pi. So 2 pi is nice because if you have a phase jump by 2 pi, you just shift your fringes by in one fringe space. It doesn't kill the coherence, so that's why we don't lose the G1. But of course, it increases the mean value. So this is, we looked a bit deeper into that. So here, these are trajectories where we remove the slope, the dynamical slope. So this is a trajectory A, where there is no phase jump, and you see the fluctuations. And this is another trajectory where you have a 2 pi phase jump, and then KPZ continues. So it's as if KPZ occurs, but piecewise. And this doesn't kill the interferogram because it's by 2 pi. It's a very small change in the fringe space. And this is here actually a whole map, so delta, the phase as a function of x, a long time. And you see that, for example, here, this is the trajectory where we have a jump. And what we see is that actually, if you zoom here, you have a pair of spatiotemporal vortices, one clockwise, the other one anti-clockwise. If you are very far from it, it doesn't affect at all the phase. If you go through the two vortices, you get a 2 pi phase jump. This is very easy to compute. So this explains why we have that. It's because of the nucleation of this pair of vortex and anti-vortex pair. So then how do you look at the density, the probability distribution? You have to sort your trajectories. You take the one that had no phase jump, and then you get the Tracy-Widom distribution. Then you take all the trajectories that underwent one phase jump, and you get this peak. And then it's more difficult because we don't have enough statistics. So we discovered that actually KPZ physics is resilient to this kind of vortices, as long as there are not too many. So this is not an experiment. These are theory results from the model that describe our system, but which tend to confirm that indeed the parameters we are playing with correspond indeed to KPZ scaling in the variance of the phase. Okay, so now it would be nice to... I thought I had an intermediate conclusion. Yes, so now we would be happy to explore this phase diagram, and this is under progress. First, what we want to do is to go to 2D. And I did not say, but 2D KPZ physics has never been observed in any system because it's very difficult to have a 2D interface in a 3D space. But here, a 2D condensate is directly a 2D KPZ system, so it's easier to do. So, debated topic. Several papers, theory papers, say that vortex proliferation will always occur and that you will never see KPZ scaling in 2D with polariton system. And then others, like our friends in Grenoble, did simulation and found KPZ scaling. There is no, I mean, it's for sure that they did exactly what we did in the experiment, and they could collapse all the points onto a universal scaling function with the parameters, which are the one from 2D. So we tried then to check actually that the model had converged, which means that the result is not sensitive on the mesh you choose for your calculation. And then we got a surprise, is that, so this is the mesh, and this is the density of spatial and spatiotemporal vortices that you observe. And what you find is that if you reduce the size of the mesh, you see the proliferation of these vortices, and you lose KPZ, actually. So actually, the conclusion is that all the theoreticians were right. The one that do more analytic experiment and consideration and consider a continuous 2D system, indeed, they find proliferation of vortices. But the one that do numerical simulation, they need to choose a mesh, and if the mesh, and the longer the mesh is, the longer your the smaller the mesh is, the longer your computation. So usually you take a mesh with a size which are relevant for polaritons. So typically around 1 micron, this is already big for polaritons, and then you find KPZ. And so the conclusion is that if we work in a discrete system, like a lattice, that's super cool, then we should be able to observe KPZ scaling. But this is so somehow the fact that we have a lattice and some discreteness of the real space imposes some cutoff for the nucleation of vortices and allows KPZ scaling to emerge. So this is what we are presently doing. So we are trying to produce the largest as possible 2D condensate, so using these honeycomb lattices, and they are working super hard to try to see KPZ scaling. And I think I'm going to stop here because we cannot go to topology, so just to make you be willing maybe to hear me one more time. So this is a honeycomb lattice, which is really beautiful because you see that we have 2 atoms per unit cell with 2 different on-site energies. So one pillar is small and the other one is larger, so that it implements this Hamiltonian with 2 different on-site energy. And then you open a gap, and then you have some Berry curvature, which we can experimentally measure. And then this is really the beginning of really fabricating a topological insulator and measuring a Chern number. But this is too complicated, so I'm going to close now. Just giving a brief overview of the main research main direction in which we are going now. So we are super interested in going a bit deeper into this physics of out of equilibrium BEC, and in particular looking at KPZ physics in 2D. Topology, so we have done a lot in the linear regime, but then there is really very interesting physics to do, trying to play with nonlinearity, and we have some papers and a lot of theory work actually going on in the group, showing that we have really a nice platform to do interesting physics. And then another thing is to go toward the quantum regime. So what I mean the quantum regime is really to be sensitive to 2 polariton interactions, so the discreteness of the number of polaritons, and trying to really explore the phase diagram of a driven dissipative Bose-Hubbard model, and trying to experimentally measure entanglement with this kind of lattices, and this is really work progressing a lot these days in the group. And with this, I would like to thank you very much for your attention.
Thank you, Jacqueline. We have questions? So,
you have to catch the ball.
Does it work? Yes, it does. So do you need the phase frustrated 1D lattice to get KPZ, or
No,
It
no,
was
no.
just you had the sample and you did the
It was a sample, and actually, if you look at the band structure, did I show it? Maybe not, but there is no. It's one lattice where actually, to have the lasing threshold the smallest as possible, we pump only the outer, the main line, and not the outer pillar, so that we detune with the blue shift, blah blah blah. You don't care. We detune this site with respect to the other one, and we destroy the flat band. So the regime in which the system is operating, there is no flat band. We need a negative mass band. That's all what we need. So it was the sample we had.
Okay, cool, great. What's the cue?
Thanks for a very nice talk. Can you say a few words about this measurement of Chern numbers?
Yes. So the idea, I'm going to go slowly. So in the introduction, I'm going to, it is an invitation for me to give the second part of my talk. But the idea is that, so topology is the idea that you have some quantities which are very sensitive to local deformation, like you take a sphere and you make you push on one side, you make like a dip. The curvature is going to change, but then you can consider very integrated quantity like this genus number, and this is going to be an integer and cannot be changed except if you dig a hole. This is our simplest way of saying this is what we use. The idea of topology is that this geometrical form that we will consider are this band structure, these bands. And so for the bands, if you put disorder, you are going to change locally the shape of these bands. You are going to change locally the energy, the wave functions, but there are quantities, which we call Chern numbers, which are integral over all the possible states, so like over all the surface of some quantity, and you can show and understand why it comes. And these quantities are these Chern numbers are integers, and there is no way you can change a Chern number without. So the equivalent of digging a hole is closing a gap and reopening it. If you don't close a gap, you will always keep the same Chern number, whatever the distortion you make, small distortion you make to your system. So, and what is important is that the Chern numbers, they are not related to the shape of the band structure. It's not enough measuring the energy of the states. You need to measure the eigenstates. These are how the eigenstates vary when you move a bit in k-space along x or along y. So to extract these Chern numbers, you need to measure the eigenstates. And so the easiest lattice we can use, so to get topology, you need at least two bands. And so the one simple system which we consider here is a honeycomb lattice. And we don't take, like in graphene, the same on-site energy because we want to open a gap, so that we have two bands which are separated and we want to measure their property. And so, because you have two atoms per unit cell, the Hamiltonian is a 2x2 matrix, and the eigenstates is a two-component vector. And to measure a two-component vector, you need to measure two angles. And to measure two angles, you need 4 measurements. So what we want is to measure the eigenstates. So for a certain k, and with our angular resolved measurements, we can probe just a single state. We want to measure the relative amplitude between the two sublattices, so it's theta, and the relative phase between the two sublattices. And with these 4 measurements, we can reconstruct the wave vector. And then with the wave vector, we can compute the Berry curvature. And so that's what, so in this sublattice, the Berry curvature, so if you, this is the theory, the Berry curvature is essentially 0 everywhere, except at these points where the two bands are very close to each other, these 6 points, and you have a positive and negative Berry curvature, so that overall the Chern number is 0, because we did not break time reversal symmetry. But this is a proof of principle. Then we want to apply a magnetic field and measure a real Chern number. So what we did is actually fabricate this lattice, and then the PhD student got a very clever idea. So he collects the light from the sample, and he's doing a real space image. So you see here, we show the lattice, and when you look in real space, this is the image we collect. And then we need to measure the relative amplitude and the relative phase between the two sublattices. Relative amplitude is easy, it's the difference in intensity. But relative phase is more complicated. And so what he's using is a device which is called a spatial light modulator, which is a liquid crystal device which you can control electrically and which can actually create a phase change in reflection. So it's a matrix of little pixels, and it creates a phase that you can control, that you can program on each pixel. And doing that, and playing with the polarization, you are able to either make so that the reflected light will have a phase, a different phase, or will be completely blocked. And doing that, what he's doing is 4 measurements. A plus B, this is the regular image that we do. A plus IB is using a pi over 2 phase difference, and then A alone or B alone. And then doing that, you can reconstruct the eigenstates, and then you can compute the Berry curvature. This is not as simple as that, but this is the simple picture. And so, for example, here you see that this is a bonding band and anti-bonding. And because it's anti-bonding, there is a destructive interference, and you don't see this band very much. You see? Whereas when you do A alone, B alone, or A plus IB, you see it very well. So you see already that this is more like A minus B than something else, okay? And so doing so, these are the measurements. I did not explain the theory, but it's exactly the same. And then you get the Berry curvature for the lower band and the upper band. And this is the measurement.
It's still a polariton lattice.
It's a polariton lattice, but in the linear regime. So it's really like photons. And then, if we want to go to break time reversal symmetry, we need to apply a magnetic field. So then we need a polariton because we want the Zeeman splitting. We want the exciton to play its role, the excitonic part. And then if we start with graphene, the regular Dirac cone, we want to use the exciton part to apply a magnetic field. And you see sigma plus is here and sigma minus is here. We have lifted the degeneracy between the two Dirac cones. And then to get a Chern insulator, we need to also lift the degeneracy between these 2 points to open a gap. And this we can do using spin-orbit coupling. And for spin-orbit coupling, we can do that playing with the polarization of the photon part. So I'm not going to go into the detail, but we can actually easily engineer a spin-orbit coupling, and that's how we can really fabricate a Chern insulator. And then we want to probe the eigenmodes, both in sublattice degree of freedom and in polarization, and so on. And then we can also probe, measuring the Chern number of a two-band model. This has been done already with very complicated method with cold atoms. But this method can be generalized to much more bands. So actually the Chern insulator will be 4 bands, 2 atoms per unit cell and 2 polarization. But then we have also theory, already the simulation showing that we can also look at the topology of a 6-band model, considering both S, Px and Py orbitals on this honeycomb lattice. And there is also a very interesting topological property, actually non-abelian topology, that we can address using our tomography experiments. So this is really the beginning. Well, this was the second part of my talk. to make a long story very, very short. Time for lunch?
May I ask a quick one? Can you say a few words about the origin of the noise term? I'm going back to the Capizzi problem in the experiment.
So the noise
creates
comes
the
from
noise
the fluctuations, actually, the coupling to the outside world. You have some quantum fluctuations. This is the most basic noise. And then you can have additional source.
The dissipative character.
Exactly. Yes, exactly.
Thank you.
But then there are some ideas that we could actually impose some correlated noise on top of that, for example, in the pump, and see if, how the scaling changes and so on. But the basic approach is really that, yeah.
Other questions? I think no, so we thank again.
Thank you.